From the dawn of humanity, our ancestors observed the persistent force of gravity. Objects, when unsupported, would plummet to the ground. This simple observation, however, led to centuries of contemplation and debate. The ancient Greek philosopher Aristotle proposed that heavier objects fell faster than lighter ones. This idea, based on intuition rather than experimentation, dominated scientific thought for nearly 2,000 years. Aristotle's influence was profound, shaping the intellectual landscape of his time. His ideas about gravity, though ultimately flawed, provided a framework for understanding the physical world. However, it would take a revolutionary thinker, centuries later, to challenge these established notions and set in motion a new era of scientific inquiry. In the 16th century, an Italian scientist named Galileo Galilei dared to question Aristotle's long-held beliefs about gravity. Through a series of ingenious experiments, Galileo demonstrated that objects of different masses, when dropped from the same height, fall at the same rate. Legend has it that he dropped balls of varying weights from the Leaning Tower of Pisa to prove his point. Galileo's findings challenged the very foundations of Aristotelian physics. His experiments revealed that the acceleration due to gravity is constant for all objects, regardless of their mass. This groundbreaking discovery paved the way for a more accurate understanding of gravity and its effects. A century after Galileo, the English physicist Isaac Newton formulated his law of universal gravitation. The story goes that Newton, while sitting under an apple tree, was struck by a falling apple. This seemingly mundane event sparked a profound realization. The same force that pulled the apple to the ground might also govern the motion of the moon and planets. Newton's law states that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This elegant equation, F equals gm1m2 over r squared, revolutionized our understanding of the cosmos, explaining everything from the tides to the orbits of celestial bodies. In the early 20th century, Albert Einstein, with his general theory of relativity, further refined our understanding of gravity. Einstein proposed that gravity is not a force acting at a distance, as Newton had described it, but rather a curvature in the fabric of space-time caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the trampoline's surface. Similarly, massive objects create dips or warps in space-time. Other objects, like planets, then move along the curved paths created by these warps. Einstein's theory provided a more complete and accurate description of gravity, particularly in extreme environments such as black holes and the early universe.